Welcome everyone. My name is Jim Chastain. I'm an applications engineer here with EasyPower. Welcome to our Thursday technical webinar. And today, before I introduce our guest speaker, as we typically do, I would appreciate it if you could help us out by providing some feedback to our poll questions. And so we want to start with a little bit of an understanding of where your focus is as far as your strategy for safety improvement at your facility. So if you would indicate all that may apply to your situation. Looks like we have an international audience today. Welcome from all parts of the world where you may reside. All right. So here's how folks have weighed in on this question. And it looks like not only are we talking to the right audience, I think it's understandable how popular this topic is. So the next question is, do you involve mobile devices as part of this strategy? And again, we're kind of talking sign of the times when more and more technology is involved in the productivity issues and facility management. We will have a question and answer period at the end of the session, but by all means, you're welcome to submit questions as we go through the presentation material. Okay, here's how people have voted on this topic. And then finally, have you heard of some of the newer parts as far as Class C and Class D GFCIs? Excellent. So let's give this about another 10 seconds. By all means, we do appreciate your feedback, and this does help the presenter kind of guide his presentation and his focus. All right, let's see how folks have weighed in on this. So now at this time, I would like to introduce the global product manager from Littelfuse, coming to us from Saskatoon, Saskatchewan, Mr. Mark Pollock. So Mark, I'm handing the presentation off to you. It's all yours.
Thanks, Jim. Thanks for the introduction, and thanks everyone for joining. Hopefully everybody is doing well and safe in these interesting times. So today I want to review electrical safety by design, and really that the heart of it is looking at some of the design steps that can be taken and to really have a meaningful impact on electrical safety. Just to give another, sentence about me. So my name is Mark Pollock, and I am the product manager for the protection relays at Littelfuse. And over the last 14 years, I've worked with a number of roles here at Littelfuse, with some technical sales, global sales, and also some business development. And really today, appreciate again you joining us to talk about electrical safety. It is a really important topic, and something that by taking a few of those design steps on the right components at the beginning can really improve the safety of the plant long term. So just to kick it off, thought I would put up a simple illustration. So I'll give you a couple seconds to read through that. And sometimes we're really not aware that there is a solution to a particular safety risk until after there is an accident. That's sometimes unfortunate that we have to use that as a post-mortem or as a after the fact to review. But it's really something that manufacturers of product and the safety managers at different facilities are really moving more and more to try to research, develop, implement safety solutions before an injury occurs. Now, even the best intentioned policies or safety instructions can certainly be misinterpreted or simply bypassed if somebody's in a hurry. So honest mistakes can be made. And really the intent, again, of the presentation today is to share some ways that safety can be improved by deliberate design and ensuring that you get the intended result. So it's really a big topic to cover in the limited time. So we'll try to present some of the highlights. Certainly, we have some more documentation available as well. We can, you can reach out if there is more information you'd like, in terms of a white paper. We do have some resources available. But what we'd like to look at are some safety control points. And these are points in the plant, in the electrical infrastructure, where you can improve safety. Older facilities might have some special concerns just because the cost to update them can seem insurmountable. But we'll try to show improvements that can be made without breaking the bank. And there was a recent study that was done that calculated for every dollar specifically spent on safety, the companies would see a return of about $3. So that is obviously a wise investment, investing in the safety of the plant and the facility. Now, some of the areas we'll cover, we'll be looking at reducing incident energy to minimize electrical shock, and finally reducing the risk by trying to stay out of the panel altogether. So a couple of quick charts that you may have seen before, but they highlight how safety regulations, they are having an effect, they are working. And the chart on the left shows the fatal electrical injuries in the US and how they've declined, since the early 2000s. And that's certainly, great news. And like I say, evidence that some of those safety regulations are having an effect. Now, despite the good news, you can also see the chart on the right that non-fatal electrical injuries have started to decline, but they're not declining at the same rate. So they're staying a little more stubbornly high. So that's something that still needs our focus. Now, when it comes to deciding how we should go about making the workplaces safer, this is a very common reference that's getting a lot of publicity, so that's fantastic. And it's the hierarchy of controls. So now a lot of the focus in the early safety programs was on the bottom 3 layers of that pyramid. So that's the personal protective equipment, the administrative controls, and awareness. And if you kind of put this into an automotive analogy, the PPE and administrative controls could be the seat belts and the traffic laws. And when you go to awareness, that would be the driver training that you receive and some of the speed limit signs. So those certainly combine to help avoid, not prevent, but they do avoid a lot of unsafe situations and reduce the severity of an injury if something does occur. But it doesn't necessarily make the car itself safer to drive. Now, I do want to be clear, I guess, on the point that all those 3 items they're critical, they're foundational blocks, and should be part of a safety strategy. But what we want to focus on are some of the more effective ways to make the workplaces safer on the top of the pyramid there. And again, those operate in conjunction with the ones at the bottom. So these are engineering controls, which would typically try to limit the fault or the incident energy, substitution, which would replace some of the existing equipment with safer options, or elimination at the very top, which can sometimes be difficult to achieve. It is possible in some scenarios. Now, the 2018 edition of NFPA 70E was released a little while ago and has a lot of great improvements. And one of those is the inclusion of the hierarchy of controls we just mentioned right on the front cover. And this was something previously mentioned, as more of an informational note in the standard, but now it's been drawn in and included, in more detail in the standard, and brings in vocabulary that some of the non-electrical safety professionals may already be familiar with. As another point, it does try to align a little more closely with what CSA Z462 also has. So it's trying to help some of those multinational corporations to have some alignment there. Now, one of the other themes, in the updated document is that there's been consideration given for potential human error. And those errors can both be conscious mistakes. So for example, somebody who deliberately is ignoring a PPE requirement because they're in a rush, there's maybe something they need to do that'll just take a second, or accidents that someone may have dropped a wrench, is the classic example, but an unintentional mistake that can occur. So given that human error is one of the leading causes of electrical incidents, the inclusion of the hierarchy of controls really directs users to try to evaluate the options they have on the upper half of the hierarchy. And if you can focus on those, it really reduces the impact of human error on safety, just because the items at the bottom of the pyramid are subject a little more so to human error. So before we get into controlling the risk, let's just take a quick second and we can define a little more about what the risk is. So there's three ways that people are harmed by electricity, and outlined here, shock. So that's definitely the leading source of injury. Arc flash, where electricity can flow across an air gap between two conductors or two surfaces that are at different voltages, and arc blast, and that's a pressure wave that is created as a result of that thermal expansion during an arc flash. So when it comes to reducing electrical hazards for older facilities, and I guess even existing facilities of any age as well, one of the first and most important tools in that toolbox is to have an up-to-date single line diagram. So it really is a key piece, and you can maybe call it the roadmap to improvement. Without that document and without that being up to date, most of the other improvements and things we can talk about are pretty difficult to achieve. We really need to start from a base of accurate information before we can move ahead to make good decisions about what to do. So there's just a quick sample of a single line diagram, of course. But once we have that information, we can then look at how we can coordinate in our system. And one of the things we can do is make sure we're replacing some really old fuses, in particular if you have renewable fuses, with newer fuse technology that is current limiting and indicating. Those products can provide better protection, particularly if you're comparing to the renewable fuses. If you're in a facility that's old enough, again, you might also have some older electromechanical relays. And these could be feeder relays, they could be motor relays, they could be overcurrent devices. But newer microprocessor-based relays, and I guess I'll use newer a little bit loosely because they've certainly been around since the 80s, but the microprocessor-based relays don't require the same maintenance personnel to enter the cabinet to maintain and calibrate the relays on a regular basis. So that's one benefit. Another, it is getting harder to find people that have that know-how on calibrating the electromechanical devices. In addition, there's more precise measurements and additional protection features as well, and those can certainly improve the safety and even communicate that device through communications to operators or other plant SCADA systems. Now, this is a photo here that a colleague of mine had took when he visited a site, and in this case, the operator was supposed to take an action if the ground fault current exceeded the pen mark on the meter. And despite that pen mark is not exactly easy to read, but this is really not going to qualify as being a great method for doing that. Now, hopefully, a lot of the facilities that you work with have been able to do an arc flash study, and if not, it's certainly strongly recommended. In some regions, those are actually required as well. But that arc flash study really helps to identify the high-risk areas. So the results of that study are then used as a ground zero point to start managing the risks using the hierarchy of controls that we've just spoke about. So when we talk about a single line diagram, One of the pieces that, of course, would be referenced there is the grounding system, the grounding method. Now, most electrical faults, and here we reference some work by Dunkey Jacobs, which the number there was 95% of electrical faults are ground faults. And as the majority of electrical injuries are shock related, and most shocks are ground faults. So when you tie it together, it really comes in to be a good place to start. Now, it's not to say that a phase-to-phase or a three-phase fault, never occurs, but in many cases they do escalate from ground faults, and only about 5% of electrical faults are not initiated by ground faults. And in those cases, the root cause can be miswiring, accidental shorting, human error would typically be some of the major drivers. Now, one type of ground fault is when a person, perhaps standing on the ground or touching something that's electrically bonded to ground, would come into contact with an energized phase conductor. And so in the residential or low power world, we have what we call Class A ground fault circuit interrupters, or GFCIs, as I'm sure you're familiar with, since the 1970s. And they really have done a good job of reducing the number of people killed at home by electricity. But then when we talk about factories and industrial facilities, often the voltages and leakage currents that are in existence in the equipment there mean that a Class A GFCI is just not going to be a viable option in most cases. So, as shown on the slide here, a Class A device is intended for systems at 150 volts, line to ground or below. And certainly there could be some three-phase 208 volt loads in an industrial facility, but the bulk of the power distribution would normally be at 480 or 600 volts. So as I mentioned, on the previous slide, you can see the graph on the right, exemplifies that the effect of GFCIs in the home has been quite dramatic in terms of reducing the number of electrocutions. And I'm sure that everybody would agree that we really would like to do the same thing at work. And on the left, you can see the levels of current that we're dealing with here. So the first line drawn out on the graph is at 6 milliamps, which is the level of a Class A GFCI. And that is below the let go threshold. So that if there was to be a shock experience that is coming through a GFCI, it's below the let go threshold so that you're still able to let go. For comparison, it takes about 50 milliamps for an adult heart to go into fibrillation. Now you can see the other lines listed on there as well, indicating that respiration is affected and difficulty breathing can occur. And just to clarify there, when I mentioned that the let go threshold at 10 milliamps, a Class A GFCI is not going to limit the fault current. The Class A GFCI will begin picking up at a 6 milliamp level. So I just wanted to make that clear. Now, what UL has done in order to give a bit more flexibility to the industry is to go ahead and create a couple new GFCI classes under UL 943C. And in the poll question there at the beginning, I see there was a few people that have begun to hear about that. And just to give some explanation to what those are, those classes, Class C and D, those GFCIs trip at 20 milliamps. So this is something that's able to provide protection for personnel, but also giving a little more flexibility for those industrial applications. So those classes, which are based for use up to 600 volts line to line, are referred to as special purpose GFCIs. So you might sometimes see SPGFCI listed, in some article somewhere. Now you might say, just hold on a second, that you thought 6 milliamps was required as a pickup for personnel protection. And how does 20 milliamps really qualify? And the answer to that is that although these new classes of GFCIs do trip at 20 milliamps, they actually follow the same inverse time curve that is defined by UL 943, meaning that the trip time of a Class C or Class D at 20 milliamps is actually faster than a Class A at 6 milliamps. So that gives protection based on that same inverse time curve. Now, one additional requirement here is for continuous monitoring of the ground conductor between the receptacle and the load. And that really protects against a hazardous voltage on the chassis of the load if there is a problem with the ground conductor or there is an open circuit in the ground return. Now, in the US, that's really what the OSHA Assured Grounding Program is all about. And what a special purpose GFCI with this function allows you to do is to automate that and continuously provide that protection. And if you compare that to the manual effort required for ground proving and how often the ground proving may be done, the automated solution can certainly be more cost effective and provide safety that's monitoring all the time. Now, another type of device that is mentioned in that standard is the Equipment Ground Fault Protection Device, with that acronym EGFPD. And that is quite a mouthful, but that name makes it clear that it's not the same personnel protection as the fixed GFCI. And that's really just because it allows the adjustment of the trip level up to 100 milliamps. Again, it does operate on the same UL 943 curve, that same time current curve, which will provide a good degree of protection for personnel even up to the 100 milliamp level, and again with an even faster trip, but only devices that have a fixed trip level at that 20 milliamp number will qualify to be called a GFCI. So here is an example of a special purpose GFCI and EGFPD that's available on the market today. So if you go back to the hierarchy of controls, a special purpose GFCI provides you with a safer substitute for the Assured Grounding Program, and for all applications provides an engineering control in terms of the actual ground fault detection to reduce the risk of shock. Now, if you're considering industrial shock protection, it's worth to make sure you're checking the standards that the products are tested to. That term GFCI isn't truly legally protected. So even if the product is called a GFCI, it's important to look for what is the UL listing and making sure that it has listed to the right standard so that you know what you're getting, so that the product is going to behave as you expect. And there's more information available on these devices on the link that's shown on the screen there. Now, one of the more important pieces of electrical safety is around the system grounding. And this, again, is a lot easier to understand with that up-to-date single line diagram. Now, starting from the left, ungrounded systems, and usually that means a delta secondary, are mostly found in older facilities, but are still being designed in from time to time for some process industries. And really, this is because of the feature that the first ground fault does not produce any ground fault current. And that allows production to continue until there's a convenient time to shut down and find the fault. Now, that advantage does come with a number of significant disadvantages. So there is a risk of transient overvoltage. There's also some difficulty in locating the ground fault. And there's also a real possibility that ground faults may be ignored for some time, depending what type of ground fault indication system is available, which can lead to some system-wide installation degradation. And that itself can mean future, more frequent faults and more escalation into phase-to-phase faults. Now, if we move further to the right, a lot of electrical systems today, especially in the US and Canada, are grounded. And with that, there's no more risk of transient overvoltage, and there is easier fault location using ground fault current with widely available ground fault current relays. And some of the particular advantages I'll get to in a minute, but one thing relating to solidly grounded systems in particular are that fault currents can be quite high. And what that results in is rapid shutdown when there is a fault, and there can be a risk of an arc flash when you have that ground fault. So if you remember that a ground fault is the most common type of electrical fault, you can see that there still is some disadvantage there, just given that that first ground fault could be an arc fault. Now, as you move to the right with resistance grounded systems, it blends the advantages of both of those ungrounded and solidly grounded systems. So a high resistance grounded, or you might hear it called, a high impedance grounded, or a system with an NGR, which is a neutral grounding resistor. Those systems can still provide continuous operation on a ground fault, and still allow a safe amount of current to flow and for the fault to be quickly located. And this allows, when you're using those type of systems, it allows you to eliminate, and if you can link that word back to the hierarchy of controls, eliminate the risk of an arc flash on that first ground fault and eliminate transient overvoltages because the system remains grounded and tied to ground. An ungrounded system that does not have an accessible neutral, it is possible to upgrade that to a resistance grounded system. And even if you can do that upgrade without having to replace the whole power transformer. Now it's done using a zigzag transformer as shown on the slide. And this zigzag transformer is connected to the bus, which creates a neutral point that can be resistance grounded. And a 3-wire solidly grounded system can also be converted to resistance grounding. And in this case, you would typically just connect a resistor directly between the XO and ground. And when I say resistor, I mean it is a purpose-built grounding resistor. It's not something you can just pull the toaster from home and wire it up. It is important, though, to make sure that equipment like capacitor banks, filters, surge arresters are rated for line-to-line voltages when you do this. On a resistance grounded system, during a ground fault condition, those unfaulted phases do rise to line voltage when the fault is present. So that's the reason for ensuring these other devices are fully rated. What's not shown on here is 4-wire system, but with those applications, if you have a distributed neutral for line to neutral loads, lighting is the most common one. Those are more difficult to convert and usually would be left alone, or we'd need to take some additional considerations. In some areas, that is not allowed by code to resistance ground a 4-wire system, or there may be other specific requirements that have to be met. So that's something that needs further review. So when we look at resistance grounding, all of those advantages that we see with the resistance grounding come with one disadvantage, and that is that the resistor has a possibility of failing open, due to mechanical damage, or perhaps due to a fault that was present on the NGR for longer than the time rating of the NGR itself. Now there's more pieces in the grounding connection as well, and those could also fail. So that could be a broken connection wire, or just a loose connection after maintenance. One other possibility highlighted here is corroded ground electrodes. And in some cases, we've even heard customers talk about stolen grounding wires. And any of those events, any of those failures can result in the system being ungrounded. Now, if you have a system with a broken connection somewhere in there, you then have the system convert to an ungrounded system. And that brings along the risk of transient overvoltage and things we talked about already. So, and something else that you need to be aware of is that then the ground fault protection on the system that is normally looking for leakage current will also fail to detect a fault because there's no longer a return path for that fault current. So in that case, there's another engineering control that we can use to mitigate that risk. This control shown here, which is a continuous NGR monitor, this we'll say is a little bit of a misnomer because an NGR monitoring device will verify the complete neutral to ground connection. So it's not strictly the NGR, but also the connection from neutral to ground, including the NGR. So in the example here, there is a sensing resistor device to provide a connection to the system, and it allows a small current to flow from the relay that is measuring the neutral to ground resistance. So since that's part of the monitoring logic, and it also facilitates voltage monitoring of the neutral as well. And as is typical with these devices, there's a current transformer shown that measures the ground fault current as well. And now once you have that package of measurements, the device can take that voltage, current, and resistance to not only verify the ground continuity, but also provide a backup that even if there is an issue with the NGR and the system is ungrounded, the rise in neutral voltage and lack of current can be used to identify a simultaneous ground fault and resistor fault. So the package of measurements allows a very robust capability of monitoring the health of the system. So just to clarify what we're meaning when we talk about the arc flash on the first ground fault and how resistance grounding can mitigate that, here's an example of a ground fault both on a solidly grounded system and a resistance grounded system on the right side. So you can see that the amount of current is going to be limited by two impedances. One is the impedance of the system, and one is of the fault. And the resistance grounded system on the right side has an additional impedance, of course, which is the neutral grounding resistor itself. So if the resistor is sized appropriately, and in most low voltage applications, that would typically mean at 10 amps or less. And with that appropriately sized resistor, we can eliminate the risk of arc flash on the first ground fault because of that additional impedance that's in that loop. So to transition to arc flash, there are certainly plenty of hazards to talk about. It's really like a bolt of lightning, an intense light, sound, and energy all packed together. And that high amount of heat, when it's discharged, it can vaporize the copper bus bar, and that creates a huge amount of expansion in the conductors in the air. So with that expansion, in a fixed space inside the panel, that creates a pressure wave that can blow apart pieces of equipment, travel at over 700 miles per hour, and of course would contain pieces of molten or burning metal and shrapnel. And in addition to that, there's the risk of the fire and toxic smoke that comes from the insulation and all the other materials inside the panel. I'm sure that many of you have seen all kinds of photos of equipment that's been damaged by arc flash, but aside from the safety risks, of course, it's the risks of the equipment which creates uptime, operations issues for the plant, and a liability as well. So the costs really can skyrocket if you have to leave the entire plant offline until a particular critical piece of equipment can be rebuilt or replaced. And as I'm sure you're aware, a lot of that critical equipment, the lead times can be measured in weeks, not days. So that can have a pretty big impact on plant operation. Now, if we're looking to arc flash and what we can do about it, first we should look at what determines the severity of the arc flash. So here we're talking about current squared and time. And the actual, that current squared in time is the thermal energy from the arc flash. But the actual system energy that's used to run motors, for example, is a function of the system voltage and current. Now, psychologically, there is a bit of a perception that low voltage, might be safer. So an electrician might think they can work live on 480 volts without, as much hesitation as they would when they're moving to a system that is, 15 kV. But really, the nominal current on the 480 volt system would usually be higher. Now, the available fault current is what can determine the amount of energy available to the arc and if there's sufficient energy to maintain that arc. And that's a function of the size of the transformer or generator supplying power. And the current is limited by the impedance of the system and also the characteristics of the arc itself, including the arc impedance, or the fault impedance, I should say. So the bigger gap, between bus bars then would mean less current if we hold all other variables the same. And the distance that an object, or person might be from that arc would also determine what amount of heat is transferred to them. So these factors can certainly be tweaked at the design phase, but they're a little bit more difficult to change after the fact. Now, if we're looking at retrofit, that leaves time, which is the focus of some of the engineering controls for arc flash mitigation. Now, in terms of design phase, one way to reduce the energy that's available to a fault is looking at a flatter topology. So we, in the example here, we're showing there's a 20 MVA transformer, and instead of using that, perhaps two 10 MVA transformers could be used to feed the two separate buses. Now, of course, if the design calls for a link between them, then the arc can be fed by both directions, and so that would not have the intended effect. Another form of arc flash mitigation that is certainly being discussed and is widely used in some applications is arc resistant switchgear. So this really acts as a permanent layer of extremely effective PPE and redirects the arc flash and the blast energy out away from the workers. So you can see in the picture here a little bit of a vent in the top corner on the side. Now this gear can be expensive and can even be a little more expensive if you factor in the retrofitting of the building to maybe vent that arc. Now when the arc is contained inside the equipment damage can be considerable as well. Now, of course, that is secondary to the human life and to the safety of the personnel that are working with the equipment. But it is worthy to note that if a door is open during an event, then of course the additional protection of the arc resistant gear is negated. Now here there's a video that's hopefully coming through all right, but really when we review some of those options, we're kind of coming back to the time again, and that's really not a consolation prize. You can see here that in these two videos, the difference that time can make. The video on the left had no fuse protection, and the video on the right had fuse protection. So it's not entirely scientific, but it just shows the difference that the interrupting time can have. So that the orange particles you were seeing, of course, were molten metal. Certainly could burn your clothing, be inhaled, and other risks they would pose if you're not using the correct PPE as well. Now, there's a few things we can talk about on how you can reduce that time. So as you saw, a current limiting overcurrent protective device can limit the destructive energy to a small fraction that could normally flow in the circuit if it wasn't used. And so I think it's important to point out that there's a few differences between some of those current limiting devices and what time factor is associated with each. Now, UL specifically has, the fuse classes, RK5, RK1, J and T, and CC, that are all considered to be current limiting fuses. However, there are some differences in the degree or levels of current limitation. So I think I want to make sure I outline current limiting as a definition. Now, UL listed circuit breakers are labeled current limiting, and with those circuit breakers, they must pass a series of short circuit tests and clear the test circuit in less than half of an electrical cycle. Now, UL doesn't impose, we'll say, different I²T limitations for those different breaker ratings. That's something you would have to work with the breaker manufacturer. And I²T that I'm mentioning there is really the amount of energy that's passing through the control device. So fuses must also clear the circuit in a half cycle, just like a breaker, in order to be called current limiting. And being a fuse company, of course, we recommend the use of current limiting fuses in many applications as one of the important things you can do to reduce the arc flash energy. Now, the slide here, the gray area under the curve, would represent all the energy released when there's a fault, when you're not using any current limiting devices. So in this case, when a current limiting fuse is used, so we're showing a class RK5 would be the first curve. That class RK5 design, the fuse clears the circuit before the first half cycle, and that will dramatically reduce the amount of total energy that's dissipated. Now, I also put on the RK1 fuse curve as well, and you can see by means of comparison, it's also a current limiting fuse, but has a smaller area under the curve and therefore less energy through. Class J or T fuses are even more current limiting, and CC and CD are even more current limiting beyond that. So by looking at the fuses you're using in the facility can have an impact as well. So as I mentioned, a while ago, it was standard practice to use UL Class H fuses, and those are known as renewable fuses. And there's a few of them around in some old facilities, and in the interest of worker safety, though, they've been prohibited for new applications as per UL. So just to kind of keep building on this, current limiting fuses, they do provide much better protection all around, and the different class fuses provide different degrees of current limitation. So when you're using, when you look at the tables provided by the manufacturer, you can see what type of current limitation you're going to get when you're looking to replace those fuses. So let's just say that the fault current on our fusible disconnect was 30,000 amps. A 100 amp class RK5 would limit that current down to 6,400 amps. Now, if you look at another fuse that's physically the same size, but designated to be more current limiting, that's the RK1, if you use that fuse instead, you could bring that down to 4,100 amps. And again, looking at class J, you could lower that even further to 3,500 amps. So there's certainly a lot of options that the design engineer has, and in the end, reducing that opening time can help to mitigate the potential arc flash magnitude, provided that the fuse curve meets the reliability requirements. So just to put this into a single line diagram, if we think back to the hierarchy of controls, we're again talking about the effectiveness of that substitution. So this is a really quick example of how substituting one fuse type for another, and in this case, we're upgrading RK5 to RK1 fuses, that can have a pretty substantial impact in mitigating the arc flash hazard. So here we're looking at, again, in the one line diagram, we can see that the RK5 200 amp fuse rating, the incident energy was calculated to be 11.6 calories per centimeter squared. And if you relate that to the PPE categories that were available, that would be a category 3. And if by comparison, you were to take that and upgrade to an RK1 200 amp fuse, which is physically the exact same size, so it should not require a change out of fuse blocks or fusible disconnect switches, the result is now that the incident energy calculates to 3.5 calories per centimeter squared. And with that, a PPE category of 1. So that's something that can have a significant impact, and that might even be in line with what the daily wear of that worker is out on the plant floor. So they may not even need to change PPE. So as we already discussed, the energy released by an arc fault is a function of time. And the longer it persists, the more energy is released. So just a real life example, if you think of, a candle burning, and if you move your finger over the flame, of course, if you move it over quickly versus more slowly, you can feel that heat energy building up. So if you want to shift from current limiting fuses and talk about another product that can be designed in to retrofit existing equipment. Now this product is an arc flash relay. And the principal idea of an arc flash relay is to limit the time that an arc persists in the event of a fault, and therefore it minimizes the energy released. So with detection and response time that's less than a millisecond, the limiting factor in that equation would be the interrupting device that's being used, and of course how well it's maintained. Most applications would be using a circuit breaker with a shunt trip input, but even if you factor that in, a typical breaker operating time that's shown there, 35 to 60 milliseconds, it still puts the overall clearing time below the typical time needed for the cable to catch fire, and can significantly reduce the incident energy compared to not having that instigating tripping device. So this shows a few examples of arc flash relays, which are designed to use light instead of current as the primary measurement to detect the arc. And each of those products has the ability to detect and trip the breaker quickly. Now, if there is some concern about high intensity flashlight or some other things like that in the equipment, because these relays use light as the primary trigger, you can also take phase current measurements and bring them into the relay and program it to use both light and current as your threshold before taking action. Now there's various arc flash relays on the market, which all work in a variety of applications. And just by example, two of the products here are capable of sending the signal to the breaker in less than a millisecond, just like we showed in the previous chart. So this can certainly be designed into new equipment or retrofitted fairly easily into existing equipment, and that will really make the facility safer, reduce the potential damage, just because now you're getting a device that can begin tripping very, very quickly. So to show, for those not familiar, just so you can visualize how arc flash relays are put into equipment, in the switchgear picture here, you can see the arc flash relay is installed on the right-hand side of the cabinet, and there's 4 sections to the gear. And here it's utilizing 3 single-point sensors, one inside each cabinet. Those are the small white boxes there, as well as a fiber optic sensor that can be installed along the bus bar in the back of the equipment. And this system will then work in conjunction with the circuit breaker to protect the equipment. So the relay will provide the arc flash protection and fault location, and then the breaker will provide the clearing. Now, upon reacting to the arc flash, that upstream breaker, there is a potential for that the upstream breaker might need to be connected to the arc flash relay, as the local breaker, the circuit breaker shown there, is also perhaps a device that could be subject to an arc flash. So with those 2 circuit breakers that would be connected to the relay, you can now have a system that has enough intelligence to trip an upstream breaker if the local breaker had a fault and did not operate. So just as a case study that I wanted to share, this showed the significance and the savings that can be achieved by designing in a product like an arc flash relay. So we worked with an end customer that had a facility where their arc flash analysis determined that their 480 volt switchgear, which was fed from a 3.5 MVA transformer, the switchgear had a PPE category of 4. And this meant that the worker wasn't allowed to approach the cabinet with the door open. Now they decided to retrofit an arc flash relay into the switchgear, and the install took only a couple hours, took 3 hours, and that resulted in the PPE category dropping down to category 2. And as it turned out, just less than a week after that installation, the plant did experience an arc flash event, and in that event, the arc started and the switchgear cables tracked up the bus. And in looking at the analysis, all 6 of the light sensors did react to the light from the arc flash, and the relay sent the trip signal as expected. And it did successfully limit the damage, with repairs costing less than $6,000 and only 24 hours or less of downtime. So the customer, in talking with them, they estimated that the downtime, without having a device like that, would have been weeks or maybe even months, with repair costs that could have approached $1 million. So implementing an engineering control like that, like arc flash relays, can have a dramatic impact on the safety and also provide some good insurance for the facility. So if we look at the hierarchy of controls pyramid, we've talked about varying levels of effectiveness that you can achieve by different design-in methods. But one of the most effective that we mentioned is sometimes more difficult to achieve is the elimination. Now, technology has advanced So remote communications, such as Bluetooth, can be used to interact with these devices. And the net effect is that the worker can talk to these devices without even having to approach the panel. And I think many of you have heard, obviously, of IIoT, or the Industrial Internet of Things, and everything from Nest thermostats in the home to touchscreen displays on white goods like refrigerators. Those are all signals that there's an ever-growing demand and interest in that data. And so now this type of technology is really, for a number of years been existing in products in the industrial space as well. So I certainly would encourage you to check it out. And I want to show one example of an overload relay. So here the MP8000 is an overload relay enhanced with Bluetooth. And this wireless communication replaces the knobs and buttons on the face of the relay and allows you to view the faults and adjust the settings from a smartphone or a tablet, at a safer distance. So the interface would then be on the app and provides very strong functionality. So as mentioned, that really allows you to enhance safety, and because now workers do not need to enter the control panel to take those readings or make those adjustments. So I just want to reiterate that because you're using an app or some other remote communications interface, that doesn't mean that you get a limited picture of what's happening with the relay. So in many cases, that actually opens the door to have more insight into the history of the relay, into some of the actions and trip events, just because you can display that information in more flexible ways in the app. So here there's a few screens just as an example relating to that MP8000 relay. And as you can see here, it still has the ability to see the real-time measured values, change the settings, and view the fault history. So all of that flexibility still remains, combined with the safety of not having to open the panel door. So if you've never used or seen a remote interface to an industrial control product, you can take a look at that link that's included there and see a demo, but it's certainly something worth considering. So just to review, there's only a couple minutes left here, but a quick review says we've used the hierarchy of controls to walk through the safety control points where the components can be used to control, substitute, or even in some cases eliminate the electrical risk that exists for the workers. Now, by upgrading components and systems in the facility, perhaps looking at resistance grounding, looking at replacing older fuses with current limiting fuses, looking at arc flash protection relays, considering industrial GFCIs or Bluetooth-enabled relays, those all allow you to design in safety. And they really don't, in many cases, they're not any more expensive than some of the typical devices you would use anyway. And even small differential, that return on safety is certainly worth it. Now, workers and business owners, they do need to be reminded that while PPE is essential, it is the last line of defense against an electrical hazard. So it's, as in the example of the automotive world, it's still an essential protection, but it should be the last line of defense. When we can design in devices that are on the top of the pyramid, it overlaps with the PPE and those kind of controls to provide a very comprehensive protection. So, in summary, I think that working together, we can certainly make electric shock and arc flash injuries in industrial environments, less common. And, even one incident can cost more than the price to upgrade. So something that's worth considering at the outset of design. So I want to thank everybody for taking time to join. And we've used most of the time here, I know, Jim, but if there's maybe one quick question that was submitted, we could take a look at it now and maybe follow up after the presentation for the others.
Yes, actually there's two on the same topic, and so I'm going to leave your screen up because you may want to refer to your slide on transformer grounding. But the question is, what is the function of the diode on the ground fault monitoring circuit on the NGR monitoring?
Sure. I'll flip back to that slide, it may take a second to update on the presentation, but I can flip back here quickly. The diode that is shown there, so I assume it's this slide here with the diode connection in the bottom half of this sensing resistor.
Yes.
So the purpose of this, it's a back-to-back Zener diode, and really that's a voltage clamp, because that is the connection point for an NGR monitor to the neutral. There is voltage on the neutral during a ground fault, and we want to make sure that that voltage does not pass through to the relay. So the resistance on the top half is very large to drop, virtually all of the voltage when there is a ground fault, but that voltage clamp on the bottom will ensure that even if for some reason there is voltage present on that center point that is unsafe, that clamp will ensure that that voltage becomes clamped to ground. So it provides protection for the control circuit that's running to the relay.
Okay. And the other associated question is, does the NGR monitoring work the same on low resistance and high resistance grounding schemes?
The monitors do work the same on high resistance or low resistance grounded systems, yes. Now, in the case of some of these relays, they need to be calibrated when it's installed and various set points put into the relay so it understands what type of resistance is expected and what type of resistance increase or drop is not acceptable. But yes, the overall design principle would still be the same for low resistance or high resistance grounding.
Thank you, Mark. I think we've kind of expired our time. It was a great job, and certainly the questions that were remaining will be answered via email for all to see. So thank you very much for your presentation, and we look forward to the next time you're our presenter. Thank you, Mark.
Well, thanks very much. I appreciate everybody joining, and yeah, happy to follow up with additional questions.
All right.